Perfect. Then? Every time. Great. Thank you everyone for being here for the third session of REBLS. I've been long involved with the workshop, and now I'm the first time session chair. And I immediately give off to talk about composability of message passing systems in a very related area. So Alfred, stage is yours.
Thank you. My name is Alfred Åkesson, and I will present ComPOS, a DSL for composing IoT systems with weak connectivity. This is joint work with Görel, Hedin and Niklas, and we all work at the Department of Computer Science at Lund University. This work was part of my PhD thesis. When programming IoT system that connects different devices, one can use scripts to mediate the messages between various components of the IoT system. We call these scripts compositions. These compositions need to account for the fact that IoT systems have a weak connectivity and that connections can go up and down. If these scripts have state, one need to handle this in the presence of weak connectivity. The handling of states in these compositions will be the focus of this talk. I will now show a scenario to illustrate how state can be introduced in composition scripts and how this can lead to problems we try to address. The scenario starts with a stateless system, and we later extend it with state. Here we have two devices, a camera that is in a garden and a TV that is in a house. In this scenario, the camera is self-firing and takes a photo every 5 seconds. We want to show the images from the garden on the TV, and the interfaces for the camera and the TV is provided by the services running on the devices. To connect the camera to the TV, we write the composition scripts that mediates the photos from the camera to the TV. We consider this IT system stateless as we do not store the photo or any other state in the composition. The script does not need it because it forwards the image to the TV as soon as it gets it, and here weak connectivity will not be a big problem. An interruption in the connection between the camera, between the composition and the TV leads to lost photos. However, when the connection is restored, the system functions normally again. To extend this scenario to a stateful system, we note that at night, when it's dark in the garden, the images are just black. So there is no reason to show the photos on the TV anymore. Thus, we change the system so that the TV only shows photos when it's bright outside. Our new goal for the system is to show images from the garden on the TV if it's bright outside. We add a light sensor to filter out the dark photos and only send the images to the TV when it's bright outside. So now the camera sends a photo to the composition script. When the script receives an image from the camera, it must first ask the light sensor if it's bright outside. It can do this by sending a message to the sensor and waiting for a reply. During the wait, the compositions need to store the image, and thus it has state. The photo the composition stores is shown here. Now the composition sends a request to the light sensor, and the light sensor reply. Then, when the result from the sensor arrives, it sends the photo to the TV. In this example, we see how the photo stored in the composition adds states to the system and make it stateful. If a reply from the sensor is lost, the composition script will be stuck waiting for a reply. We need a mechanism to handle this situation so that the system is responsive, at the same time does not store a lot of data due to stuck programs. In this talk I will present the abort semantics, a mechanism for managing state in compositions. What our abort semantic does in this scenario is that when a new message arrives, it removes the current stuck composition state and starts processing the new image. The abort semantic is designed in the context of the service composition architecture. To explain the service composition architecture, I will expand this scenario. Here we have a schematic view of the example with the services camera, TV and light sensor, and the composition A connecting everything. We add an extra camera, and we also add an extra light sensor and the composition B, which combines the behavior of the sensors to provide a so-called synthesized service. The synthesized service allows the composition to provide an interface with the combined behavior of the light sensors. Now let's more explicitly introduce the service composition architecture. The service composition architecture has three concepts that are important for this presentation: the services, the compositions, and the devices. Services provides functionality but don't know to whom they talk. Instead, their functionality is accessible through an interface that the compositions connect to. The composition composes the services in a system. Compositions are specified in a domain-specific language. In this talk, this language is ComPOS. Compositions can be used to combine multiple services into so-called synthesized services. And in this example, B combines the light sensors 1 and 2. It's through synthesized services we can connect composition with each other. Here, A connects to B via the synthesized service. The devices host the instances of the services and the compositions. A device is a running instance of the middleware software. One device in the architecture often corresponds to one physical device. So, the compositions are specified in the ComPOS DSL. On this slide, I will give a brief overview of ComPOS, and on the next slide, I will show it in an example. The ComPOS DSL sets up connection to the services and then coordinates outgoing and incoming messages. It has no support for computations. Instead, computations are delegated to the services. There are 4 control flow constructs in ComPOS: sequence for doing one thing after another, select for handling alternative responses, parallel for waiting for responses in parallel, and finish first to wait for one branch to finish. ComPOS is implemented on top of the Palcom middleware, and the Palcom middleware uses the service composition architecture. Here we have the system again that shows images from the garden on the TV if it is bright outside. In the middle is the ComPOS script, and during normal execution of the script, the camera will spontaneously send a photo. The composition will receive it, and the photo here matches the first line in the script. This is an outer when clause that waits for a message named photo sent from the service camera. When the composition receives a message that matches a when clause, it will execute the body under it. A script can have multiple outer when clauses to wait on different types of messages. When a when clause matches, it creates a reaction. A reaction is a runtime activation of the ComPOS script, and a reaction consists of program counters and variables similar to a stack frame. Here, the program counter is shown as the arrow here, and the reaction is down here. And in this case, the reaction contains the value P, that is the photo. And the whole state of the composition is determined by the set of reactions that it has, and that is what we want to manage. The composition sends a request to the request check light to the light sensor, and now it waits for a reply here, and a composition can handle incoming messages either by resuming a reaction like here, or by creating a new reaction when we have the when clause. The reply from the light sensor arrives and the reaction resumes. Last, the script sends the picture to the TV. When a reaction is removed, all its associated states is removed as well. So by removing a reaction, we can remove a stuck composition. So we will now look at different alternatives of handling ongoing reactions when a new message arrives. Suppose there is an ongoing reaction waiting for a response from the light sensor. What should happen if a new photo message arrives? What should the composition do? We have 4 examples of strategies for handling this situation. With the ignore strategy, we ignore a new message because we already have a reaction running. With the queue strategy, we put the incoming message in a queue and wait for the current reaction to finish before starting a reaction for the next message in the queue. In parallel, we execute the 2 reactions concurrently. With the abort strategy, we abort the currently running reaction and start a reaction for a new incoming message. The abort strategy is the approach we chose. However, a naive implementation of the abort strategy could lead to some undesirable behaviors. One issue is that messages from different sources should not abort each other. For instance, if 2 cameras simultaneously send a photo to the same composition, one of the reactions will abort the other in a naive implementation. In our implementation, we want messages from different sources to not abort each other. Also, messages sent in the same reaction should not abort each other. For example, if a reaction sends 2 messages in parallel to the same synthesized service, one of the reactions at the synthesized service should not abort the other. Many similar but more complex situations can arise in network with multiple interconnected compositions. To mitigate these challenges, our implementation of the abort strategy only lets newer related messages abort a reaction. To do this, we introduce epochs, and an epoch consists of a place and a time. In our case, the place is a connection indicated by P, and the time is a counter indicated by the subscript T. We tag both reactions and messages with epoch. An incoming message with epoch PT prime aborts a currently running reaction with epoch PT if and only if they are, for from the same place, i.e. p prime and p are equal, and the message is newer, that is p prime is larger than t. T prime is larger than t. Now I want to show two examples to illustrate how the epochs work. For this example, we will show the example what happens in a system when camera 1 sends an image. For this example, we call the two connections from the cameras to A for strawberry and ice cream. It starts with the camera 1, which sends a message with the image of the on the connection strawberry to the composition A. When A receives the message, it creates a new reaction with the epoch strawberry 1. Reaction A sends a message to B and tag them with the epoch. Upon receiving the messages B starts a new reaction with epoch strawberry 1 and sends a request to the light sensors 1 and 2 tagged with the epoch. The light sensors measures the light and respond. B then combines the result from the light sensor 1 and 2 and replies to B. B combines the result from the light sensors by replying that it's bright if any of the sensors says that it's bright. After replying, B ends the reaction. When A gets the result from B, it sends the image to the TV and ends its reaction. In the second example, we have the same system, but the timing of the messages will be different to show the abort strategy in action. It starts like the example from before with a message from camera 1 to A. Then A sends a message to B, and B sends a message to the sensors. At this point, A and B awaits responses and can potentially be aborted. What happens now if camera 1 sends a new message? A will create a new reaction with epoch strawberry 2. This new reaction will abort the old reaction because strawberry equals strawberry and 2 is greater than 1. A will also send a request tagged with strawberry 2 to B. The message sent to B will create a new reaction that aborts the running reaction because the new epoch aborts the old. The message sent from B will now have the epoch tagged with strawberry 2. Now camera 2 sends a message on the connection we call ice cream. This message starts a new reaction with the epoch ice cream 1. Composition A now runs two reactions. They do not abort each other because they are from different places: strawberry and ice cream. Next, composition A sends a request to be tagged with epoch. B creates a new reaction and runs it in parallel. And that's the end of this example. So, to conclude the abort strategy, it removes obsolete reactions without the need for timeouts that need to be tuned. Removing reactions is important when we have a weak connectivity because otherwise it's easy to accumulate a lot of obsolete reactions. The abort strategy also processes the freshest message immediately, making the system responsive. We are pretty sure that we can statically determine if a system has a bounded number of simultaneously ongoing reactions, and this is a problem we have started to work on. However, one drawback of the abort strategy is that it can be too eager and abort reaction that would have finished otherwise if one waited a little longer. For example, if the light sensors are slow and the camera takes photos quicker than they can respond, we might end up in a scenario where all reactions are aborted and nothing reaches the TV. You can find more in the paper. For example, the paper thoroughly describes ComPOS, describing all the constructs and the syntax. The paper also describes how other strategies like ignore, queue, or parallel can be implemented with the abort semantics by using an additional special service. In this paper, we also evaluate ComPOS with the abort strategy by successfully implementing 7 home automation scenarios proposed by Rodriguez Avila et al. The paper also includes a small performance evaluation using a macro benchmark, and we measured the round trip over Ethernet, and for ComPOS it was around 1.7 milliseconds, and in a pure Java implementation of the same composition it took 1.6 milliseconds, so the Java implementation was 5% faster. Thanks for listening, and I now welcome any questions.
We already have any questions from the audience? So, hey.
I have been a little bit lost when you have presented your language with your 4 constructs, parallel, first, all these things. I am not so sure where are they executed, or which language are you describing? Is it for the green boxes or?
Yes, it's for the green boxes.
Okay, and in that part, you don't need preemption or abortion in the language itself? For instance, you could decide that you are executing things in parallel, and for any kind of reason you want to abort something or you want to kill some computation?
So the language itself does not have any computation, so to say. You just do the message passing. So it doesn't have loops and stuff.
Finish is a kind of abortion. When you receive one, you kill the others.
Yes.
So you don't feel the need that you have a dedicated construct for doing this kind of abortion. You don't need that.
No, but it may be something that would be needed.
Does the, first of abort all other than the first one?
What?
There's parallel and then something else that was first. Finished first, yeah.
Yes, but it's so if you have here we have a picture of them. So if you have finished first, you can send like a request to a service, and you send. So how this would execute is that you do the send and you do the send, and then you wait for any of them, and the one that will come first, you will not do anything here, and you will continue to execute here.
Hello. So in languages like ambient talk and E, you have this notion of a far reference. So it's a pointer over the network, which points to something which is far away. And there is like hidden in the concept of the programming language level, there is a buffer that takes care of intermittent connections. Would it be fair to say that this is like kind of an algebra to combine far references? that allow you to do meta programming and make very complex very complex far references.
Yeah.
Because there you also have the notion of leasing. If you send messages over a far reference, you add a time interval, and when the time is up, the message automatically garbage collects.
Okay.
That's one of the things that we have.
So in this architecture, so my name is Boris Magnusson. I'm from the same university. Is this on?
Yeah.
Yep, sorry. So if you take up one of your slides with the green and the architecture, here is, I mean, this can be used both within the same device connectivity, where it's less likely that things get lost, but it can also be used, but some of the more complicated ones. So this on the right hand side, these are far references if you talk Wolf, but the one between the camera and A is a near reference. So if one of the things that are far, for example, some of the light sensors are lost, the connectivity, there is in the underlying architecture the notion that there is a timeout between these devices, which means that the connection is lost and everything is removed. So they're not there forever, but it's sort of a part. That is part of the architecture itself. How long timeout you want to accept?
Not it is.
Yeah, so it is in the architecture, not in.
And is it transitive if they refer to each other?
No, it's in every connectivity, so to speak. So if you and so I think that explains your question perhaps best.
Yep.
Yeah.
Questions? Then I get to ask mine, which is somewhat related. I was wondering about the parallel composition. Can you, if you parallelly compose things, mix, I guess, transactions from different origins, like strawberries and ice cream, or can you not mix them for parallel composition?
You cannot mix them because the when here is what like says this which the connection is, and then this is in the context of that epoch.
Right. Do you think that would be useful for, say, future extension of the language?
Maybe.
Very good. Any further questions? Otherwise, I think we're also good. Any next speaker can set up?